We're going to talk to you about deep learning with drone imagery. We're going to give you a really specific example, which is mapping tree crowns, how to pull tree crowns out of drone imagery. But the the technology and the approach that we're going to give you today is really flexible, and I'm excited to hear about how you might want to be using this. So let's do our code of conduct. You guys have seen this probably before. We are all here together as a community who love data and love exploring data, and we want to make this fruitful and enriching. And so we want to build this community. And as part of that, all these participants, like you, you accept to abide by the UC Love Data Week Code of Conduct and accept the procedures by which any code of conduct incidents are resolved. I'm sure you've seen this slide before, but let's make this a fruitful learning experience for all of us. Please use welcoming and inclusive language. Please be respectful of different viewpoints. Please gracefully provide and accept constructive criticism, focus on what's best for the community, show courtesy and respect towards all members. So thanks for letting me show that. It's important that we do build this community across UC. It's very exciting. All right, so before we launch into the technology side of today's talk, I wanted to tell you a little bit about where we come from. Shane and I and a few others on the call, we're all part of the University of California Division of Ag and Natural Resources. This is a network of people across the state throughout all counties in California that do work around agriculture, natural resources, nutrition, youth development. This has a long history in it's an American institution that brings information from the universities to communities and back again from communities to universities. We do this through many ways. We are organized around several statewide programs. If any of you are familiar with 4-H, that's part of what UC ANR does. We have Nutrition Policy Institute. We have a lot of these wonderful programs. And our program that we're part of, the Informatics and GIS program, is one of these core programs. And our goal is to help you integrate cutting-edge geospatial tools into your work. We do this through training, through services, through research, and we have a pretty extensive drone program. And so we're going to be showing you some of the fruits of that work in the research and drone domain in this workshop. But if you're curious at all about what we do, please connect with us. And if you're interested in the wider group, this is us. It's a small group. You're going to meet Maggie, that's me, and Shane. You're going to meet Shane soon. But we provide a lot of workshops like this outside of UC Data Week, and we also have office hours. So if you're interested in following up with us, please do so. All right, so I'm going to get on to the core of the program now. We're going to separate this into two sections. The first part is going to be me, and I'm going to set the stage and give a gentle introduction to these deep learning approaches and how they can be used in high resolution mapping. I'm going to do this through giving one specific focused example, and that is our use of mapping orchard tree crowns from high resolution drone imagery. And we did this experiment with pistachio trees. I'll show you more in a bit. And we imaged this orchard through time. So we wanted to test how these algorithms worked over space and over time. So the first part's going to be me setting the stage. The second part is going to be Shane, and that's where he's going to give you a deep dive into the process of using these deep learning tools in Pro. That was him just waving. And so our goal here is to set you up so you can do this yourself. You're not going to be doing any hands-on work right now because to do deep learning in Pro takes some additional software installation, and it does take time. So rather than that, we're going to give you a complete workflow. Shane's going to walk you through that process. and give you enough, to go out and experiment yourself. We're going to also teach you all the kind of tips and tricks and corners to cut that we've figured out. So with that, while I'm talking, Shane will be watching the chat. While Shane's talking, I'll be watching the chat. So if you have any questions or anything, please do put that in the chat, and we'll have time for questions after I'm done and time for questions after Shane's done. All right. So this is be part one. So this will be my gentle introduction into deep learning. So the figures on the left you're going to see a lot. This is some high resolution RGB, red, green, blue drone imagery flown throughout the growing season across a pistachio orchard outside of Davis. This is June imagery. It's really our best quality image. The trees are really leafed out, the shadows are minimized. It's a gorgeous little slice of imagery. And we're going to show you in this workshop two workflows. One is going to be MaskR CNN, which is a CNN, and I'm going to explain what that is in a moment. MaskR CNN is a fantastic little workhorse. It does an amazing job, and it's commonly used. We're also going to give you show you a workflow for a relatively newer process called Segment Anything, the Segment Anything model, or SAM. And that also does an amazing job. So these are going to be two workflows that we're going to talk to you about. But before we do that, let me just set the stage again. So we're talking about remote sensing of trees. That's our goal, is how do we pull trees out of high resolution imagery? So let's set the stage and talk really quickly, one slide about remote sensing for pulling out objects out of imagery. The latest and greatest method are these convolutional neural nets, or CNNs. I'm going to tell you a little bit about the basics of them. What are they? And then I'm going to showcase them in this project. And then we're going to go on to the deeper dive. So the paper that I'm going to illustrate or bring a lot of our examples from is here. It's open access. If you're interested in it, we can send it to you, but it really does walk through all the steps of this work. We, in this paper, evaluated 3 CNNs. We're only going to show you 2 of them because one of the 3 that we evaluated really did a poor job. So we did MaskR CNN, SAM, which I told you about. And we also did YOLO, which stands for You Only Look Once. I'll explain what that means in a moment. And it did the poorest job. So we're not going to show you that one because we sort of used that as a setup to show how much better the other ones were. But let's set the stage. So when we're talking about remote sensing of vegetation, vegetation has this unique spectral signature healthy vegetation looks a particular way across the electromagnetic spectrum. And so because of that, it allows us to do many things. We can classify imagery, we can look for change, we can understand the condition of vegetation, we can get at ecosystem components like canopy cover or biomass, we can get at structure. But what we're going to do today is talk about object detection. How do we pull out individual objects, especially from high resolution imagery? And this approach is really useful to understand start of season, end of season, how phenology is changing, how vegetation trees are growing. And in a lot of cases, you can get yield estimates from size. So this object detection is a really important step in the remote sensing world. And the methods for object detection can be split into manual and automated. And on the manual side, this is just on-screen digitizing, where you basically take your mouse and try to avoid carpal tunnel syndrome by delimiting all these little things in your image. We still do that. In a lot of cases, we have to do that to gather training data, but boy, is it tedious. And then on the other side of that spectrum are automated techniques. And automated techniques can be rule-based or they can use learning techniques. And so on the rule-based side are a whole class of algorithms called object-based image analysis. And these were really hot stuff, 10 years ago. And these were where you develop a series of rules to say this tree is going to have this shape and this size and this kind of spectra, and you pull out objects that way. But that's really being taken over by these deep learning approaches. And most popular and most efficient are these CNNs, convolutional neural networks. These are multi-layered models that learn as they go to pull out these shapes. And I'm going to show you, I'm going to talk about trees, but there's so many cool examples right now. I mean, these are examples from some recent papers, using CNNs to pull out sharks from drone imagery, CNNs to count cattle across a landscape, or CNNs to look at fruit and understand quality of fruit. These are just a handful. And indeed, if you go onto the Esri website and do a search for CNN models, Esri has provided you with so many pre-trained CNNs. And this is just a snapshot of an entire page. But you look at the snapshot, you've got car detection in the USA, car detection in New Zealand, and that's because they're trained slightly differently on slightly different imagery. Tree detection, ship detection, pool detection, Arctic seal detection, human detection, building footprint, windows and doors, parking spot. So these CNNs are just everywhere, and the target objects are really they're vast. I mean, they're anything that has a distinct shape and size that you can see in the imagery. We can try to pull that out and analyze it. So when you dive into this, it all gets a bit confusing. I mean, it's, there's all these figures out there, input layer, hidden layer, output layers, there's all these terms, AI, machine learning, CNNs. And then you get a little bit deeper and there's these, kind of crazy sounding stuff. There's hidden layers, there's backbones. What the heck is going on? So that's just our goal here, is to just kind of provide you a gentle introduction to these things and just to, get you started so that you can see how they work with high resolution imagery. All right, so what are they? CNNs are bits of software. They're an algorithm that is implemented to find objects. They are the basic building blocks for the computer vision task of object detection. How do they work? They work by learning all the aspects of an object. So they basically are going to pass this kernel over an image, and they find from training data, ooh, that tree, it tends to have an edge like this, or it tends to have a shape like this, or it tends to have this kind of color. And every step that it matches a trained image correctly, it gets a little bit of incentive to go further. And so every time you're moving through this algorithm, through these layers, you're resolving and resolving and resolving these individual features. And like I said, this process can have many layers, and the layers are just where the algorithm learns all the little bits, all the little aspects of that particular target object. And so let's first ask here, what is a convolutional kernel? And if you've done any remote sensing in the past, convolutional kernel is just like a filter in remote sensing. We've used these all the time. Back in remote sensing, if you've had a remote sensing class, you might have done edge detection or sharpening or smoothing filters. These are little filters that move through your image. In this case, those are the numbers in the filter, and each time the 3x3 pixel or 3x3 filter moves, it runs that operation and gives a yield pixel in the middle. And so the smoothing filter, for example, just, smooths out all of the detail. The sharpening filter makes the detail sharper. The edge detection finds the edges, etc. So these convolutional neural nets are really, really similar. And I just took a snapshot from this great website, 3 Blue 1 Brown. So this is just the idea of this kernel is moving through your image and coming up with some kind of output. That's all this is. It's just a little 3x3 or 5x5 or some size filter moving through your imagery and doing something, some mathematical function. And so the basic workflow then is you have an input image, and often you have training data. And that training data in our case was trees. That training data is passed into this model, and the model has something called a backbone, and it's going to learn those trained objects. At each layer, it's going to say, I got it, and it's going to condense it, and then it's going to pass to the next layer and go, I got it, and then it's going to move. It moves through this model process and derives output objects. And after the output objects have been created, there's a finalization process where you validate how well did I do. And each one of these steps can be kind of you're overwhelmed with choices of what to add, what to put in ArcGIS Pro. So we're going to kind of walk you through that a little bit, but let me chunk it up here. So at the first is the training section. You're going to have to decide, does the model need labeled training data? And labeled training data just goes, this is a tree, this is a tree, this is a tree, or this is a car, or whatever. Does the model need labeled training data? What format should it be in? Because every model takes different format. Can the model be pre-trained with other imagery? And that's going to be important soon. Should the training data be split into training and testing data? And how should that split be made? So these are all things that you're going to think through. Then you get to the main model part, and the model is going to chunk up the imagery to deal with it. It's going to, separate. It might do it in regions. It might do it in smaller chunks. The model is going to use something called a backbone, which relates to how many layers it has. And Esri has a lot of backbone choices for you. And then you're gonna need to understand all the different arguments that it needs, and particularly in terms of training data. After you get the output objects, different models produce different kinds of outputs. I'm going to show you that. And then finally, you're going to want to do a validation process. And that validation process is pretty standard, but it's useful to go through it as well. All right, so we're going to do a series of close-ups. I told you I was going to tell you a little bit about training, and Shane is going to go into this more. You're going to see it in action, but in many cases, you are going to need to separate your data into training and testing data sets. That's if you have data on your target, like trees. And then your training polygons are going to be used to train the model, and your testing polygons are going to be used to validate your results. And the training step is really interesting because, so here I've got a snapshot. We've got an input image, and we've got these training polygons. You're going to push those into the model itself, and the convolutional neural net, like I said, is this little box or filter that's moving through, and you're going to have to make decisions about how big that filter is and how big its padding around the side should be, and what's the size of each stride. So when it moves from this set of pixels to this set of pixels, how big is that step? And that process is going to give you these candidate objects, and then the processor is going to tell you, okay, let's go find all the rest of them. And so Shane's going to talk about this a little bit more, but we discovered in our work and in this paper for our tree crowns that with a lot of trial and error, we developed this guideline on how to train the model. You give the chip size, which is 3 times the mean width of your target object. The tile size is your chip size plus 32 pixels. And the stride distance is about a quarter of the tile size. And so if this is like, what the heck? Don't worry, it's going to get clearer here. All we're focusing on here is this training step. Most models require you to come with some training data. The next close-up I want to give you is a simple, really streamlined idea about how these CNNs came into being and how they are evolving extremely quickly. So the very first CNN was in 1988, and it was called Le Net, and it was very simple, and it sort of stayed dormant for a while, but then 2012 onward has just been a boom. So in 2012, we got our first deep CNN, which had 8 layers. 2014, we got what was called region-based CNN, which meant it chunked up your image and acted on these different regions. In 2015, we got this kind of intricate way of creating these residual blocks and these really cool backbones, which do some fancy math in the layering part to speed the process up. In 2016, we got this SSD, the single shot detector, which basically didn't need to regionalize regionalized anything. It just went in a single pass. 2018, we got this cool named one, YOLO, you only look once. It's another one of these single pass, and it's really spawned this whole version of YOLOs, YOLO 2, 3, 4, 9. And then 2023, this big development, which was the segment anything model from Meta. And so if we just go through, some of these, this 2012, we had the first deep one, then we got regions, then we got residual blocks, then we got backbones, then we got single passes, and now we've got this pre-trained SAM. So this is just evolving really quickly. I just wanted to give you a sense of how deep this is. Oh yeah, and then the next year, Sam came out with text prompts, which still to this day blows my mind. So you don't even have to, you just put in, what am I looking for? Tree. So cool. So Esri right now implements many of these. It implements faster RCNN and mask RCNN. Those are both region CNNs. It implements a bunch of different backbones, including ResNet 101 and ResNet 152. That relates to how many layers and how fast or slow your process is going to be. It implements YOLO version 3, and it implements SAM. And we're going to show you, results, or we're going to show you how to do these two, mask RCNN and SAM. I'm just going to highlight a little bit about SAM because it is just about the coolest thing. This is a model developed and was published by Meta in 2023, and it is pre-trained. So they pre-train it with millions of images. So instead of you having to come with all your polygons to say, this is a tree, this is a tree, this is a tree, you can just throw SAM at your data set and it does a pretty good job. So Esri really quickly implemented this in its model portfolio. But this guy, an absolute genius. If you look him up or if you're interested in stuff, he's the one who really took SAM from Meta to a new level and made it text promptable. So, when we are going to show you this, you just type in tree, like tree crown, which is very cool. All right, so another CNN close-up is the output objects. I said before that different models produce different types of outputs. So early on in the CNN process, you would get this sort of a heat map, which was, the probability that this pixel was a tree. That was work primarily, or done in eCognition, which is a great object-based image analysis software suite. Some models, including Mask and SAM, produce realistic polygons, so they try to really trace the outline of your object. Some, like You Only Look Once, and others produce a bounding box, a rectangle. So you want to make sure that the model that you're choosing suits your output needs. And then finally, validation. So you've gone through this whole process, you've chosen all the right, things, you've played around enough. Now you've got your objects and you think they're in good shape. Well, how do you know? And so the validation step is really important. And this is where you have separated your data into training and testing data. And then the process is really relatively straightforward. It uses common validation metrics that were derived for binary data. So it basically says, did my polygon that the algorithm found, does it match what the testing data? And if there's no match in terms of this IOU, which stands for intersection over union, there's no intersection here, there's no match, so it's a false positive or a false negative. But then you can see, yeah, I'm starting to get better. This intersection over union is pretty great. And so you typically assign a threshold here of about 0.5. If half of your found polygon overlaps with your predicted polygon, then it's pretty good. It's a true positive. And so the metrics are derived. There's a suite of metrics that you can derive really easily from this. And this slide just is a graphic example of them. This little white outline here is a false positive. So the algorithm found a tree, but there wasn't one. This is a true positive. There was a tree and the algorithm found the tree. And then this is a false negative. There was a tree and the algorithm didn't find the tree. And most validation tools will give you, from those false positives, true positives, and false negatives, they'll give you precision, recall, F-score, and average precision, which are just various combinations of those three measures. So this is what it's going to look like in Pro. You're going to input your image and your training data. And so you're going to run it through this workflow. The green polygons are actual Esri code or processes. So, and Shane's going to show you all this. So you're going to basically input your data and your training data if the model requires it. You're going to train the model. You're going to run the model. You're going to output the objects, and then you're going to compute the accuracy of the model. I'll give you a quick snapshot of what we were trying to get at with this paper, just to set the stage. So in the paper, I told you before, we were evaluating 3 different CNNs. We looked at Mask-R CNN, Segment Anything model, and then YOLO version 3. And we were lucky.
Huh?
Oh, they just decided not to summarize.
If you guys could please mute, that would be super helpful. Thanks. We were lucky in our work because we had every single one of those tree crowns delimited using an object-based image analysis process. So we could really easily split that data into training data and testing data. And so, again, what we wanted to do was look at all these different models, these 3 different models, and evaluate them on high resolution drone imagery across a growing season. And so we had multi-date drone imagery. We had imagery from March through December. And you can see here, this is for pistachio trees. And we had this reference data set, which was wonderful. So we had each of these tree crowns delimited. So then we could, use these tree crowns for training and for testing. And so interestingly, this is just a quick snapshot. As you go through the growing season, in the early growing season, there's not a lot, there's no leaves on the tree. So all of the algorithms fell short. But you can start to see how you get slightly different results based on the algorithm that you choose. You get a little bit more definition in some of them. Obviously with YOLO, you get, you're just getting that bounding box. But I'll show you some other examples. So this is our June image that I showed you before. Really lovely imagery, minimum shadows, all the trees leafed out. Mask RCNN did a pretty great job. It missed a few trees in the middle. YOLO did an okay job, but Sam just did a fantastic job. And this is with zero training data. Sam just went in and said, I got you. I got all these trees, which kind of was a bit of a revelation. However, there are some lessons learned here from this process. We also show you this one. This is from August, and you can see in the raw imagery there was a little bit of haze, and this came from fires that were burning nearby. And so the none of the CNNs did a great job recognizing the trees when they had a little bit of spectral confusion provided by that haze. So they all did a not a great job. And you can see that both Mask and Sam that had done really well in June really kind of fell short in August. And then interestingly, in December, when the trees are now starting to change color and these pistachio turn, really vivid colors, from the green almost to yellow to really vibrant red. And so Mask did a decent job because it had been trained. We had trained it on December imagery, but Sam did a terrible job because I think because it was just not, it didn't have enough pre-training on the sort of tree variation. And Sam also tends to do a poorer job when the object in question has color changes that are internal to it. So it has a little, it really struggled in December for a variety of reasons. All right, so let's take a step back before we move on to Shane. Let's take a step back. Why do we care about this? And I think one of the reasons we care about this is there's so much drone and high resolution imagery out there. And so this practice or this protocol for extracting individual trees or rooftops or farms or rocks or animals, it's just going to be more and more important. And so we want to, make sure we're on top of that technology and using it to its best advantage. All right. So before I get you started, before we shift gears and move to Shane, I want to show you, I showed you the workflow model in its sort of generic sense, but this is what we're going to be doing when we do the deeper dive with Shane. The workflow kind of moves from left to right, and the top orange box includes the workflow for Mask and YOLO. We're only going to be doing Mask today because both of those require training, and a lot of CNNs do require training. The purple box over here skips all of that. That's the SAM workflow because SAM just dives straight in and it says, I have been pre-trained on millions of images. Let me at your image. Let me see what I can find. And so Shane's really going to walk you through those two workflows to get you started. But before we do that, may I ask if there are any questions? I see there's some stuff in chat, which I can't see until I stop sharing. So what do we got here? Cool. Okay. Are you validating on features, objects, or scenes? Yes, good. So you're validating the objects. Derek, do you want me to go back and go over that, or are you cool?
No, that's good. I just had a question about the resolution of the feedback, like at what level you give the feedback to the model when you're training it. So you're like
Oh,
you're scoring it on individual object matches, not like feature matches or whole scene matches.
yes, yes. All
Cool.
that feedback happens in the backbone section of the model.
Cool. Thank you.
But the validation at the output, that's when you're saying this is a true
Yeah.
positive, false negative. That's the analyst is doing that validation.
Yeah, but on each whole object.
Each whole object,
Got
exactly
it.
right. Yeah, and that just it does this intersection over, how well does your training polygon overlap with your found polygon. Great, thanks for the question. Anybody else? Any other questions that you have or anything?
Hey, Megan, can I add one
Yeah.
thing?
Yes.
We're not doing YOLO today is YOLO really, at least version 3 only does bounding boxes.
Yeah.
The newer versions, version 9, 11, wherever they are today, are now doing instance segmentation like we're doing on everything else. But Esri hadn't implemented that yet, and it's still not implemented at the level we're going to be teaching you today. So
Yeah, and
that's why we're not covering YOLO.
this is a good, thanks, Shane, for the reminder. There's so much to do outside of Esri too. We just wanted to give you the workflow within this playground because it's kind of, you can go from start to finish, but there's so many other ways to do this stuff. So, like Shane said, YOLO version 1 million will be out next week or whatever. And it just won't be implemented in Esri yet.
Yes.
Okay, great. So if we
one quick answer, Maggie, someone asked the question, how many polygons are recommended for training?
Great, yeah.
Esri, when I posed that question to them, the more the better. They're like 1,000 would be ideal or more. So
Yeah,
keep in mind, the more training data set, more training polygons you can give, ideally the better your model may be. So
yeah. For the models that require training data, they always just say more is better. I know that's super frustrating, but when you start to get into this, you're going to understand it because they need the algorithm needs to see the variability of your target, right? So yeah. Okay, great. But again, Sam, like if your imagery is really pretty great and your objects are clear, Sam's going to be a good way to go. Okay, so Shane, I think we're ready for you to take
are we
over.
going to give 5 minutes?
Yeah. Do you guys want a 5-minute break? Thumbs up, thumbs down. What do you want? One thumb, woo, lots of thumbs. All right. Let's have everybody back at 1:45.
Yeah.
Is that good?
Welcome back, everyone. Shall we get started?
Let's do it.
Okay, let me get rid of my video panel and so forth. Okay, so let's build off what Maggie just showed and let's delve into using deep learning inside of ArcGIS Pro. So the first thing that you can probably guess is in order to do this, you need to have ArcGIS Pro installed on your machine. The most recent version right now is ArcGIS Pro 3.6. Just a note for those of you who may not know, ArcGIS Pro can only run on Windows-based machines. They need to be 64-bit, which in this case, most are. Most Windows machines are 64-bit. And you need a graphics card, preferably an NVIDIA card, and the deep learning libraries installed via the deep learning libraries installer for ArcGIS. And I have a link at the end of the presentation, a QR code, so you can, if you want, you can download those and install them into your ArcGIS Pro installation. So inside of ArcGIS Pro in the last 5 years or so, Esri the company who makes ArcGIS, has been building more and more functionality into the tool, into the software that uses deep learning. Whether it's traditional image classification, whether it's object detection, and so forth. They have built a lot of these technologies to use deep learning. And what we're going to discuss today is really instance segmentation. And what I mean by that is when you do object image classification, everything gets classified, let's say, as a tree. Everything gets classified as a road, but you don't have individual objects defined that have their own unique ID or anything like that. They get a raster classification of tree. So when we do instance segmentation, each instance, each polygon has its own attribute and its own ID. And that's what we're going to be doing is instance segmentation. And at any point add to the chat window if you have questions. And the people taking the questions, if you want to bounce it to me, feel free to. I have no problem with that. So like I said, we're going to deal with instance segmentation today. So Maggie's already mentioned this, and I'm just going to highlight it again. Today we're going to work through the SAM workflow, which is pretty straightforward, simple in terms of what we do inside of ArcGIS Pro versus a mask RCNN workflow, which is more in depth. There's more work that we need to do as a developer, as a programmer, as a GIS professional. And that's mostly going to be in the exporting training data and the training of the deep learning model. But the one thing I want to point out is one thing Esri has done when they've built these tools into ArcGIS Pro is they've made it easy for us to dip our toes into deep learning. We don't have to know about TensorFlow or all these Python packages for doing deep learning. They have basically put a wrapper around that and made it easier for us to really delve into deep learning and start applying it to our use cases without having to be a high-end data scientist who understands how all the different layers and backbones and everything work. We just need to know they're there and that we want to use this one. And we can often find that out just by going through the literature, like we're all good at in UC, doing research, being like, ooh, I like that. They use that on this paper. Here's what they did. Maybe I can do that in ArcGIS Pro. And in a lot of situations, you can. And Maggie had a slide that showed which backbones and stuff were implemented. Even since that slide, which isn't that old, they have since implemented even more. So some of those that you had like the higher numbers, like the ResNet, they now go all the way back to like ResNet 18. So they're implementing more and more every day. In fact, I reran all my scripts just yesterday. Some things were broken. I had to fix it and figure out what changed. But basically, every day, every version of ArcGIS, they're implementing something more or tweaking a model and doing things like that. So it's a really iterative process. So let's delve in real quick. Maggie mentioned Russell Ranch, the Russell Ranch study area. This is a large university research farm outside of Davis, California. And like Maggie said, this is a specific pistachio plot. Here's the shape of it right now. And we divided that plot into training data, as you can see here on the right, and validation data that you can see here on the left. What we tried to do when we split this plot, we had the same number of trees in both the validation and training data set, so that we could easily have polygons for training, and we'd also have polygons for ground truthing of the validated data that we produce with our models. And the ground truth data and the polygons that we use are also split between training and validation. Here is the training data of the object-based image analysis of the polygons. And then comparably, here is the validation data set derived in the same way. So let's dig in a little bit about segment anything. Let me show you where it resides. It's on the ArcGIS, it's called the Living Atlas, ArcGIS Living Atlas, and they have pushed up hundreds of deep learning packages. Here's an example for text SAM. And one thing I want to point out here is they tell you how to use the model. And notice here, you can't fine tune it like we can do with pre-trained, like the models we create. They also tell you what the imagery has to be. And something of real importance to you when you go to use these models, and these are any of the models that Esri has pushed up to ArcGIS Living Atlas, they have a guide link. And I point this out because they walk you through using it, but not only that, they tell you what tool to use to perform your inferencing. The reason I point this out is if you were to look at ArcGIS Pro, and you go to geoprocessing under deep learning, you can see they have a bunch of different things here for doing deep learning. And if you use the wrong tool, you are going to get errors and the tool is not going to work. So I just wanted to make sure that you guys are familiar with digging in, seeing what's required for the model to work, the deep learning package, and what tool to run. Does that make sense? If not, please put in the chat window. So as Maggie said, the segment anything model was developed by Meta. It's trained on billions of images. And it was further built out by Esri to work within their system. Once again, the data has to be 3-band, 8-bit imagery. So if you have multispectral imagery from your drones, you cannot use segment anything. You could probably convert your raster, your 16-bit raster data from the drone. You could convert your red, green, and blue into 8-bit and use it that way, but you can't use 16-bit or more than 3 bands. That's where you really need to train your own model and develop it that way instead of using a canned model that is on the ArcGIS Living Atlas system. So we can go in, and if we want to use the SAM model, we are going to go in and follow this workflow here that Maggie's already pointed out. We're going to use 2 main tools. The first one is just detect objects. We don't have to train. We don't have to export training data, nothing like that. And then based on the results, we are then going to compute accuracy based on the Obaya validated polygons that I showed you a few seconds ago. So in here, what we're going to do is we are going to start the tool and we are going to get access to the deep learning, the SAM model so that we can use it. And I just want to point out 2 things. The first is you can easily go in and download the model right from the item inside of the Living Atlas. Or even easier, if you go to Portal and then go to Living Atlas, you can actually search for deep learning packages. Or you can even search just for SAM, and you will see text SAM will be the first thing you can use. And you can open that up and use it directly from there. Okay, so you've now gone in, you start the process by starting the detect objects using deep learning. In this example that we are just going to show the outputs of, we are taking just the defaults. So we're going in, we're opening up the tool, and it's going to ask you for the raster layer that you want to use. In our case, it's going to be the validation data set, the validation raster for the left side of the Russell Ranch plot. The DLPK, or the deep learning package, we are going to bring in from the Living Atlas, and that is going to be text SAM. And the only other thing we are going to change is in the text prompt, we are going to type in trees. Nothing else. No training data, nothing. You hit go, it's going to take probably less than 5 minutes, and you're going to have a result that looks like this. One thing that Maggie mentioned when she gave her presentation a few minutes ago, that we had an amazing output from typing in trees using SAM. And we did have an amazing output. What we have noticed is as they go in and they modify and they tweak and they do different things with the deep learning packages, you don't always get the same results, which can be a little perplexing. So in this case, the number of polygons returned or number of objects returned is less. You can very easily go in and modify some of the parameters and drastically improve your results. One of those could be cell size. One of them could be another value called padding. And by doing that, you can very easily, by making one change, double the number of objects you return from this one tool, or even improve it more than that. So just so you know, they make it easy with SAM, but you have to play with it once you start using it. And that is the case really with any of these deep learning models that you either develop on your own or that you use from the Living Atlas. It's an iterative process of tweaking and modifying minor parameters and seeing what the impact is, just so you know. So how did we do? So Esri also provides an additional tool called compute accuracy for object detection. And this kind of gets at, I think it was Derek who asked the question about what we use for validation. So we're using the Obaya polygons, and then we're using this tool inside of ArcGIS called compute accuracy for object detection. It wants to know the objects you're going to assess. Then you also tell it the ground truth data, which would be those Obaya polygons. You tell it which, oh God, I just forgot the name of it. intersect over union, what IOU you want to be considered a viable that consider accuracy. And if you take the default, it's 0.5. And this tool report will actually return a PDF report as well as a table inside of your file geodatabase. You hit run, and then what you get within a minute or so is a table that tells you the class, the precision, recall, F1 score, average precision, true positives, true falses. I'm sorry, I just realized I was not in my slides.
I'm sorry, I was just about to tell you. I just noticed. Sorry, Shane.
That's all right. No problem. You get true and false positives as well as false negatives. So you can see how well you perform. One thing that we noticed as we went through this process is that when you run these models, SAM or even MaskRC, and then when you develop your own, is that you do end up with sometimes small, very small polygons that you don't even notice. They're less than 0.01 square meters. I mean, they're very teeny. And if you don't dissolve them or clean them, do some post-processing, your true positive, true false, your values of true positive, and false negatives are not going to match your polygons, just because you have all these small artifacts. So sometimes you do have to do post-processing and remove the really small items. Also, sometimes it produces overlapping polygons or null geometries. You can have very, very, very small geometries that further Esri tools will say there's an error in your data set. So you have to fix the geometry and then you can run the tools. So there are some caveats when you first deal with the outputs of any of these models. Okay, so that's the whole workflow of working with SAM. Really straightforward. It's really easy to do. Questions on SAM?
And maybe if we have time at the end, you could go back over those little tweakings that seem to help Sam.
Yes, can
Yeah.
definitely do that.
Yeah.
Okay, so SAM is easy. Like I said, they give you an easy way to dip your toe into deep learning. If you want to go more in depth and do more things, then you really have to do the full workflow, which is what I'm going to show here with MaskRCNN. As we mentioned, the big change is going to be in these items right here. It's going to be the input image, training data, exporting of training information, and training the model. And these take a bit of time. They take resources, both memory and hard drive. So this is really intensive. You want a really powerful computer to do this, but it works amazingly well. Reasons to do this, as I alluded to earlier, is if you have imagery that is 16-bit, multi-band, you're not stuck with just red, green, blue. You could have a custom image stack which has canopy tree height, elevation. You could have 7 different spectral bands or more. You can have all this other data in this raster stack, and you could then use that for your training and your inferencing. So you can have a much more robust model than what you could do with the standard deep learning package. So there are definitely pros to using and developing your own models. Okay, so let's go through this process. So once again, as you saw as the previous one, I flipped the steps, put them on the left, and I'm just going to walk you through. So here, one of the new tools that we're going to run is going to be called Export Training Data for Deep Learning. One thing to note is that every type of model, whether it be YOLO, whether it's the equivalent of SAM, or if it's MaskRCNN, they all require a slightly different flavor of training data. So when you run this export training data for deep learning, you want to keep in mind what type of model do you want to run, and then you have to choose the appropriate metadata format. And there are many, and you can hover over the tool, and it'll tell you which ones you need for which type of model. For MaskRCNN, the type of metadata that we need to use is RCNN masks, and it basically goes out and it chunks up your data into chips, and it assigns a labeled raster to go along with it, and I'll show you that in a second. We are going to merely take the defaults for this run right here, And those defaults are a tile size of 256 pixel by 256 pixel. And it has a stride, or how far it moves between taking chips, of 100, I believe it's 128 pixels, both in the X and Y direction. So it just slowly goes piece by piece and goes through all your training data and snaps images and labeled images. And these are what are used in the training steps. So what does that look like? So you end up with a folder that has a folder of images, a folder of labeled images, and then you have a JSON file that explains that is used in the training process, as well as some other information. What the images look like are the following. So it looks like the images themselves are 3-band images, 8-bit, just like the original, and it's just chopped them out 256 pixel by 256 pixel. And if you throw at, basically you'll end up with, I think it's considerably more chips than you have polygons, just because of the stride and how it does it. But for each image, you have a corresponding labeled image as well. Down below here, you can see there's this red piece that corresponds to a tree up in the image above. The other, and that would be labeled as 1. The second one, you have an image up above labeled in red below. That's another tree that's going to be 1. The next item is going to have 2 labels. They labeled the little bit of an image, the little bit of a tree in the upper left, as well as the larger tree in the lower left. So each one of these get a unique label within that image. And then these images are all used in the next training step. So keep in mind that this folder with chips and tiles was created by the export training tool, and now that's going to be used in the training deep learning model. The train deep learning model tool. So let's go to that next. And stop me if you have questions. Okay, so now you created your chips, and like I said, you can have many bands or as many as you want. It'll create an image with that band stack for you, as well as a labeled image that you can then use in the training step. So you go in, you open the tool, you point it to that folder that contains all the chips, JSON file, and everything else. It reads that into the tool, and it figures out that you're trying to do something that's going to use mask RCNN, or more accurately RCNN. And you tell it where you want it to be saved to. You tell it how many epochs, so how many times you're going to work on training the model. You also tell it how much or how many workers you want to establish. And a worker is if you only have one, it'll spin up one worker who's going to take a chip, process it through everything it's going to do, and then release it, take another chip, and it's going to process it. So it's going to go through each one of the chips that you have and try to improve the model. If you give it more batches, you give it a bigger batch size, let's say you take the default of 4, they'll have 4 workers working on 4 chips at a time. You could crank it up to 12, 16, 24 or more, but every one of those batch workers takes up resources on your computer, both in CPU and GPU. So if you allocate more than your system can handle, you will crash pro and you'll have to restart. So initially, just do the batch size of 4 and do an epoch of 1 or 2. And also check your backbone and make sure your backbone is set low. So if we're doing mask RCNN, you most likely want a ResNet background or backbone. The default is, I believe, ResNet 101, or I think it's 101. But for the initial test, go down to ResNet 18 if you don't have really complex data. Run it with one or two workers or a batch size of 1 or 2, just to make sure you're not going to kill your machine, and with an epoch of 1 or 2. If that works, crank it up a little more, add a few more workers. See where your limit is on your machine, and let's say it breaks at 8, then give yourself 6 workers so you know you can process it, and then crank your epochs up to 100, 200, or 400 or more. and make sure that at the very bottom, there is a check mark down there where you can say, process, train until the model no longer improves. Check that, and then what that does is it'll train until the model stops improving and then stop. So that it could hit that trigger at 50, at 250, at 500, but it'll stop. So you won't just keep training and training for no reason. So the training deep learning model tool is probably the most time-consuming tool you are going to run. And this is one of the main reasons we're not demoing this specific thing, is because training the deep learning model tool, even on my computer, which is pretty beefy, can take a half hour to an hour. If you really crank it up and you're doing really large chips and tiles and a lot of data, it could take many hours, if not overnight, depending how large it is. So this is a really expensive process. So once you run this, what you end up with is a folder that contains a deep learning package that you can run in ArcGIS Pro. You end up with an EMD file, which you can run in other deep learning software as well as ArcGIS Pro. And you end up with a model metrics HTML and a folder that has model characteristics. And in that folder, you have an image of the chart you see on the right, a text file that explains what backbone was used, what the learning rate was, and so forth, as well as the individual images that show you on the left what the ground truth data looked like versus what the predicted model looks like. So right off the bat, they give you an idea of how well your model does or how well it performs. I'm only showing you a small subset of the images that model metrics HTML shows you. I believe by default it's either 8 or 12, but you can get a feeling for how well your model's doing. So if you're happy with this, then what you can do is continue with the next steps that we have already done, but in the case with SAM, but we can do that with MaskR CNN. So we go in, once again, we open the detect objects using deep learning, and we are going to accept all the defaults. Once we open that deep learning package model or package, we open that up in detect objects using deep learning. It is going to populate the graphical user interface with a list of all the different parameters that you can set. Keep in mind, like I said, we are going to just use the defaults for right now. You fill that out. You do the same thing you did before. You specify where you want your output to be, and take the defaults, hit go. And what you're going to see is this would be an example of the model output. You can see that this actually performs quite a bit better than the SAM model. SAM ended up with roughly, it was roughly 22%, or an average precision of 0.22. So let's see how we did here. So after we remove those really little, really teeny little polygons, dissolve them to make sure there was no issues with null overlapping or null geometries. We do the compute accuracy using the output as well as the validation data set of the object-based image analysis, and we compute the accuracy. So before we had roughly, it was 0.22 with average precision. Now we're up almost to 0.70. So we have improved dramatically the outputs compared to SAM. But keep in mind, we are training this specifically on a pistachio grove, very near where we're going to be inferencing the data. And you can see our values of true positives, false positives, and false negatives. So this model is doing fairly well. One thing Maggie pointed out earlier was that we have a rule of thumb that we apply, which had to do with tile size, chip size, and stride size. We have not taken that into account in this run. One thing where you can tell that's an issue is we have square trees. If I was to zoom in, you can see there it looks like bounding boxes. It's just a square tree because that tree is bigger than the size of the chip that was used for training. So they're coming in as squares. So we need to change the chip size. We need to adjust the tile size and the stride to really try to better better encompass the irregular shape of the trees and to just do a better job of seeing those. Okay, so let me see what I've got. So I'm going to be open for questions, but I just want to point out, you can see the difference between the SAM workflow and the Mask RCNN workflow and the results. So SAM is really straightforward and easy to use. Mask RCNN isn't that bad to use and bad to set up. You have to develop your own training data, however, to use it well. And you need a lot of training data. One thing I didn't go over is they have actually made a tool inside of ArcGIS Pro for capturing training data, which is basically you draw a polygon and then you attribute it as whatever class you're going to be developing. And if we didn't have the Obaya polygons, we would have had to manually go out and train. And right now, the models we're creating are based on a little over 400, training polygons. So we're doing okay with the number of training data sets we have. One thing I want to point out also is, we mentioned that some of the Esri models are behind the development of new ones, like the YOLO is a good example, where we only have up to YOLO 3, but they're up to at least 11 or more. Esri in the last year has come out with additional deep learning packages on ArcGIS Living Atlas, and it's called Hugging Face. There are now these things called, there's a repository that holds and tracks deep learning models, and it's called Hugging Face. Why it's called that, I'm not sure, but they actually have a model you can download. You open it up to detect objects, and it gives you an opportunity to put in a unique ID from that Hugging Face repository. And you can then use those additional models without having to build them yourself, and you can use more cutting edge models. I just wanted to point that out. And Esri is always building new models. The community, including people like yourself, like we could publish the pistachio model up to ArcGIS Online, and anyone could use it. So this system we're showing you today can also be used to add to what people need to know or want to learn. Derek, yes.
Yeah, so let's say you had trained a model and you were reasonably happy with its accuracy and you wanted
Yes.
to deploy it at scale. How would you keep track of whether it continued to be accurate? Do you just need to, as you like, if you use it on like a lot of data sets and you couldn't like verify everything, would you just like spot check, or do you just really need to like retrain models for different
Ooh,
purposes,
really
even
good
if they're
question.
slightly different?
Really good question. The first thing at scale, what you could do is you could easily, let's say we had another pistachio grove, which there are many in California. Um, if you had imagery, you could use this model on any other pistachio grove. You could try it and see how it works. But let's say you have this is working well in pistachios here, but in the other place there's something different, right? You can do another process called transfer learning, where you can, in the training piece, you can actually start from an existing model and improve on it. So you could say, here's new training data. I want to improve this other model. You say this is the deep learning package. You put it in as an input, and then you can build on and further tweak the underlying convoluted neural network structure and weights and everything by using your new data. And then you can use that in that new area, or even try and see if it performs better than the original.
But the point, I also think, Derek, part of your question was
Oh,
how do you validate, when you've gone away from your original
ooh,
training data? And
Yeah.
I mean, you can't get away from the fact that you need validation data.
yeah.
So that's the challenge with all of this, with all remote sensing. I mean, you can say I trained on this small area, I have a reasonable expectation that it's going to perform as well elsewhere, but unless you have a validation data set, you can't be sure.
Thank you, Maggie. I missed that part. Absolutely right.
But it's I mean, it's worth playing with because yeah, I mean, this transferability question is is perennial, we always want to start small and go to scale. So, and this on the screen, these are resources if you want to get in touch with us. That's our website there.
Yes.
office hours and other things. And then this paper, you can find the paper there. And then if you want to jump in, the deep learning libraries that you'll need to install are there.
Yes. And the deep end isn't too deep. It is
Yeah.
doable.
Yeah,
Um,
totally doable. Yeah, so Derek, yeah, that's just what I was just talking about. Um, you use SAM to, run and get your candidate polygons, do some checking of those, make sure they pass your sniff test, and then you take those and put them into mask as your training. We have seen that done too.
But
yes.
you could you also like set your parameters and stuff for the model? Like, does Sam have opinions about like what this tile size should be and
Oh,
stuff
this
like
is a
that?
No,
great
they
question.
really don't. That's
They
the painful
don't.
thing.
Yeah, and Shane, there's a couple. So in this, we're going to publish these slides. You'll get them through the UC. There's some supplemental slides that Shane's added, and
Yeah.
so with Sam, you're tweaking something. It's just called padding. It's not
Yeah.
called chip size, tile size, and stride distance. It's just called padding. So it's not like you can learn from Sam what those things should be, unfortunately.
Yeah. And one thing is when you look at that guide and that guide I pointed out, it tells you what the cell size was of the imagery they developed it on. So you can go in and then potentially you can modify padding. One thing we were able to do to get really good results with Sam is you can change the cell size of the of what the tool is going to use so that so that as far as it's concerned, it's the right cell size to use for your data. So there's the two things with SAM. You can mess with cell size and really padding is probably the only one they otherwise expose. They only give you just so much you can do.
Yeah. But the lesson is start small and play around and be patient,
Yeah.
right? Would you say,
Absolutely.
Shane?
And don't do a really huge image right off the
Start
bat.
small.
You
Yeah.
take a small subset of an image and work with that before you tell it to work on the whole thing. Because if you're dealing with something like if we were doing imagery at the resolution we are here, which is, God, I want to think
2 centimeter.
it's like 2 cent. It's not very big. If we did that at like the size of, not that we ever would, but of Yolo County, you'd be churning forever. So, start small. That way you can tweak things, make sure you're getting good results before you ramp it up to a much bigger size.
Yep.
And I will say that the deep learning packages on ArcGIS Online, you can use those in the cloud to infer from their data sets if they're set up correctly. So you don't have to have the data on your machine. You could use data in the cloud as well.
Awesome. Well, any other questions or comments? Andy has put in the chat. We would be very grateful for your feedback on this. It helps us and it helps UC Love Data Week. And I hope you guys all had a great time and you're going to have a great weekend before this storm moves in, at least in Northern California. I suppose
Exactly.
we're all over the place, but
Thank you all for attending today.